set set with BD. So you see the Cartesian product of B and B is equal to, you see, you order, of course, you see you have B, that is BD, and then what we have is B, B, and then BD, and then DB, and then DD. So we don't have DD here. That is the ordered pair DD that should be there. All right, I think you can see that. So you need that is D comma D, yes, the ordered pair that here. But again, you find that you have the intersection of the relation that is in A, of course, that is from A to B. You can see that when we don't have the DDs, and therefore when we have the intersection of these and the whole of these up to here, you're going to see that we don't have BB, we have BD, yes, that is it. And I think we do not have DB in that order. We don't have also DD, and therefore that remains, right? Yeah, that is okay. And if you remember what we mentioned last time, just please let me go back. I think there are some fellows who want to be admitted. Or Brian, oh yes, a number of fellows. Brian has raised his hand. Is there any issue? Or you want your colleagues to be admitted? Let me see. Okay. Oh yeah. So as you can see, last time we talked about types of relations, and these are the ones that we talked about. We talked about binary relation, equality relation, universal, sorry. Universal relation, void relation, or rather what we call the empty relation, or null relation at times, yes. Inverse relation, and yes. Key ones, key types that I wish to ask you to be very careful about are what we call the inverse relation, and especially the binary relation, because there are quite a number of instances that we shall come across what we call the inverse relation in whatever we shall do this evening. So it is important that you remember very well that the inverse relation, what it does in that case is that it reverses what a relation has done. You see a relation from A to a set B. Then the inverse in that case denoted by R inverse, written this way. R superscript -1 is that which relates B to A. You see, it relates B back to A. Therefore, you notice that in the inverse relation consists of the pair yx, such that xy is in the original relation. So I think one of the cases that we talked about was that if the inverse relation is greater than, then the original relation is less than. And I think in some of the cases we talked about them, there we are, and then we extended further to restriction of relation to a set. Then now we shall talk about properties of binary relation. And in particular, in that case, we're talking about binary relation. Now, these properties are very important, and it is crucial that at least you have a grasp of this, because you'll not only apply them here, you'll apply in many other areas that will come across even after this unit. So it's important that at least you have a good grasp of that. Let me hope that is exactly what you're positioning yourself to doing this evening. So one of the properties of a binary relation, and of course, don't forget a binary relation, how does it look like? You see, it is, you realize that it is a relation from, that is in, look at this, that is in A, you see, what we mean in that case is that you see, look at this, we have A cross A, and then we call this a binary relation. We are relating members of A, and you see that X is are related to Y, and that is whenever we have, of course, that is the members of that same set. That is what we call a binary relation. So let's look at what happens here when you're talking about this. So let me ask you to observe something even before we start with the first property. Look at what we have here. We do not have two sets. You see, look at this. We do not have sets. You're saying that we do not have two sets. Look at that. We just have one set. You see? Look at that. You have to see that. And it is important that you have that and note that clearly. And therefore, it is in agreement with what we talked about in as far as a binary relation here. You will notice that it is a relation in one set. And you can see that where we pair members of the same set in a manner that we have, that is those members related in one way or the other. That is what involves what you call a binary relation. So it is important that we have that. Now, these fellows who get in 10 minutes after time, I think you know the rule that there are certain times that if you get in beyond that, then you shouldn't be admitted, but it is okay. Let me hope that that will be okay on your side. So here we are. We have now the properties of a binary relation. So we are confining ourselves to the first type of a relation. And we're told that we have the first property that is what we call reflexivity. If anything, this is at times referred to as reflexivity property. So when do we say that a relation is reflexive? We're told that a relation R is said to be reflexive if each element in that relation, that is in A, sorry, if each element of A is related to itself. Look at this. That we're saying that for every member of A, the set A, every member is related to itself. And you can see that is exactly what we're saying here. And what we need to have here is that this one is cross A, right? That one is in that. It is not in. You can see this one is, look at this. For every pair in the Cartesian product of A and itself, then we see that A is related to itself. And we told that, yes, as a relation R in a set A is not reflexive if there is at least, so what you need to do is in that case is that you identify at least one element that is not in the ordered pair, right? Look at that. That is not in, you see, if you can identify only one element that is not related to itself, then you remember what it means is A is R related to itself, right? Well, let me hope that that is something that you've known, and especially with respect to what we did last time. So let's look at an example. We have the set X, which is 1, 2, 3. And the relation given here is 1, 1, 1, 2, 1, 3, 2, 2, 3, 3. So for every member of X, we see that every member is related to itself. This one is related to itself. One is related to itself. Here you see 2 is related to itself, and 3 is related to itself. And therefore, we say that this relation is reflexive. And that is exactly the argument that we presented here. A second case, this one, there is no C here. We let A be the set of all members of a family. Then what do we see here? That we let R be defined by is a brother of. Yes. We're talking about that A consisting of members of a family. And we told that, okay, we let R be defined as is a brother of. So if we pick one member of a family, we would want to see whether that member of a family is a brother of himself or not. And for sure, we see that there is no any given time that you talk about an individual being a brother of himself. So, so what happens in that case is that this one is not a reflexive relation, because you can see any brother A in A is not a brother of himself, or A is not related to A for every member of A, and therefore R is not reflexive. Let's go to symmetric or symmetric, whichever way you would want to pronounce. Sorry. Let's go to symmetric. In the case of symmetric relation, we say that R, we let R be a relation in a set A, and you see R is a subset of course, the ordered pair where we have A equals A, the Cartesian product of members of A and A. Then R is said to be symmetric if, look at this, whenever A is R related to B, B is R related to A. So we have a case similar to commutativity here. You see, we are not calling it commutativity, but if you remember, commutativity property, like under the set of real numbers, A plus B is equal to B plus A. This is commutativity property under commutativity under addition. Commutativity under addition. So you realize that it's similar to that, but it is not the commutative property in this case when we're talking about relations. What we're talking about here is what we call symmetric relation. And here, symmetric relation, we say that as a relation is symmetric if whenever you have A related to B, or rather two, there is an element related to another one, then that other one is also related to that other one, to the first one. So here, you notice that for this to exist, and I think this is something that you agree, you see, can only exist if, look at this, if there is the inverse, because what takes B back, what relates B to R is R inverse. If you remember, look at this, the inverse relation. Look at this. R inverse, the inverse relation is y comma x for every xy in R. So it therefore means that there has to be a condition, that a necessary and sufficient condition that a relation is symmetric is that R must be equal to R inverse. And therefore here a relation R is not, here we're saying there is an extension of what if it is not symmetric or asymmetric. If there exists two members in that if it is a relation, we have these brackets. If we have only A comma B, then we're talking about in X or in A, because we're talking about the set A. But if you have brackets, then this is an ordered pair that is in the relation. We say in this case, A is R related to B. And we say that it is not symmetric or asymmetric if there exists, that is a pair where we have A R related to B, such that let's see this. Let me modify this to make it better, and I think I'll correct this. I think I'll deal with the correct that. No worry. I think I'll send you another. Yes, another set of notes, especially the corrected ones. There is a typo here, and this typo is attributable to this. That you should be talking about a pair in A, because then you see two elements in A. Yes, you can see now we're talking about that is in area that is acceptable. We say there exists two elements of B that are related, and if they are, that is, if you have A are related to B, that is how we read this, then B is not related to A, right? That is what we mean by, you see, the notation here represents B is not related to A. So we say that it is not symmetric or asymmetric if there is a set of two elements in B in A, or such that the first one is related to B, but now B is not related to A. In simple terms, it does not satisfy this. If that is the case, then there is a time we say that that relation is asymmetric. We have an example to illustrate that. We have the say we let A to be the set of all students in a class, like in your class, SST 102, and you're asked to determine R that stands. This R stands for the relation is a classmate of on a set A is a symmetric relation or asymmetric. We notice that it is symmetric. If we pick, let's say, two members of your class, SST 102 class, and then we talk about one, let's call one of you A and the other one B. Then A is a classmate of B. And you notice that it doesn't matter how we go, we could even say the second guy is a classmate of the first one. And therefore we see that that relation is symmetric. You can see that. We say, you see, this A is a classmate of B, then B is also a classmate of A. And therefore we see, therefore, that BA is in the same relation. And thus, AB is equal to BA. And if this is the case, therefore, we see that R is symmetric. If we look at this, set A, with the elements 2, 5, 6, all the way to 15, and R is the relation is triple of 2 is triple of 6. No, 6 is triple of A. That is okay. But you see, 6 is triple of A. If we slot in that here, you see we have 6 here, and then we have triple of A. So we have 6 here, and then we have 2 there. That is true. 6 is triple of 2. But if we would want to start from here, 2 is not triple of 6. You see, it is a third of 6. It is not triple of, and therefore does not satisfy that. This is the case. It means 6, 2 is in R. You see, 6, this one is in R. But you see here we say 6 is triple 2. But 6 is not in R because 2 is not triple 6. That is it. So this one is not there. And you can see here we are using those notations. The good thing is that we reminded ourselves about these notations, and you see that we're using them regularly. So I'm happy that at least we reminded ourselves that. That is good. So now, there is something I would want you to get a difference from. In this case here, in the case of symmetric, we say that whenever you have A R related to B, then there has to be B are related to A. Right? Now, how is it different? And we're saying that if A is R related to B and B is not R related to A, meaning that B, A, this pair is not in R, then we say that it is asymmetric. Now, how is it different from antisymmetric? And this is something that I want you to get the difference, whether there is any difference or not. Look at this, and this is something that I would wish to have each one of you synthesize and try to figure out and see whether indeed there is a difference here. A relation R in a set, yes, we have also R, yes. Then R is said to be antisymmetric relation. If A is R related to B, whenever A is R related to B and B is R related to A, then A can only be equal to B. I'm allowing some brief pause for the purpose of digesting that. Different from this, we're saying here that if A is related to B, then implies that B is related to A. But in antisymmetric, we say that A, whenever if A is related to B and B is related to A, then it is only possible if A is equal to B. This, therefore, takes us to trying to figure out, to test whether this is asymmetric or not. We shall deal with symmetric and whether it is antisymmetric or not. But I want you at your own time to check whether this one is asymmetric or not, and to see whether then the term asymmetric relation and antisymmetric relation are one and the same or different. Let A be the set 1, 2, 3 that continues, and R be, of course, there is a a set of ordered pairs that are related, pairs of elements of A that are related by divides. We say X divides Y. And you're asked to determine whether R is antisymmetric or not. If X divides Y and Y divides X, when is this possible? When is it possible that X divides Y and Y divides X? It is only possible when X and Y are equal, because that is when two members of the set of reals, or any two real numbers R can divide each other. It can only be the case if they are equal. That is when you can say X divides Y and this one divides X. And therefore, we see that this relation here is, the question is this then, is it antisymmetric or it is asymmetric? And our conclusion in this case is that R is antisymmetric, because then it agrees with the definition of an antisymmetric relation. And as I've told you, an exercise in this case is that test whether asymmetric or not. And that is when now you're gonna have the difference and get to know that yes, indeed, there is a difference or not. Let's go to B. We let A to be a set of elements 2, 3, no, 2, 5, 6, 7, all the way to 15. And RB, the relation, is triple of O. Yes. And we're told here that 6 is triple 2, but 2 is, I don't know, I think we've already talked about that. Yeah, sure. Yeah, that is asymmetric, and I think we've talked about it is here. It's more of a repetition of the same. But again, now, you see, we've talked about this antisymmetric. Now, this is the exercise. Test whether it is asymmetric or not. Now, in this case here, test whether it is antisymmetric. Test whether it is antisymmetric. So in this B, test whether it is antisymmetric. Test in this A, test whether it is asymmetric or not. This is a general question. Are the following relations symmetric or asymmetric? These ones, I think you can read those ones on your own. Now we've talked about symmetric, asymmetric. That is something that you should be able to read without much ado. And even I think there are examples, and therefore kind of please go through that. Let's go to transitive relation. And in the case of transitive relation, there is something that I wish to draw your attention to here. This is some kind of a transition. When we are having a transition, you notice that there is, you see, there is a connector from one state to another one. And in this case, the connector is B. Look at this. Let R be a relation in a set A, then R is said to be, no, transitive. This one is transitive, sorry. That is also another typo. This one should be transitive. I think, yeah, I'll save this one so that I can correct, I think, immediately, and then I'll send you so that you can update. Kindly please, for everyone that is there, kindly know that there are some typos that then I may have to correct those ones so that at least reading things that make sense. So here we see that R is said to be transitive, a transitive relation if whenever A is R related to B and B is R related to C, then A is R related to C directly. So the connector in this case is B, you see. So here we look at an example so that we have a better understanding. We let A, this is a subset of the set of real numbers. where R is a set of real numbers, and you're asked to determine whether the relation is X that consists of the ordered pair XY, where X and Y are real numbers, and Y is greater than X. Okay, Y is greater than X. Is it transitive? And in my view, indeed, it is transitive. You see, if you pick any three real numbers, and you have the first one to be, the second, look at it, like in this case, we have ABC. This one's, you see, we're picking members of the set of real numbers. If B is greater than A and C is greater than B, let's even take an example to 5, 11. You see, if 5 is greater than 2, 11 is greater than 5, automatically 11 will be greater than 2. You see, but again, if you are to show this, you are supposed to use what has been given here. You are not supposed to go to specifics. And that is why in this case, you can see what we've done. And what we've done in this case is that if A is greater than B, okay, we've talked about A to be greater than B, and B is greater than C, therefore A is greater than C, yes. If A is greater than B and B is greater than C, A will be greater. That is clearly, of course, the case that A is greater than C, and therefore R is transitive. Now let's consider how many straight lines? 3 straight lines on the Cartesian plane. These are fellows who are not serious, honestly, at the moment. But anyway, let me just admit them. Probably maybe fellows are having a ride at the moment. Again, because you see, getting late by 30 minutes is too much, but it's okay. I'll admit my students, there's no problem, but kindly please improve. Next time, please don't be this late if you've joined. Oh yeah, you can now join. Victoria Mutano, you are joining too late, 25 minutes to time. Kindly please improve on that. So here we're talking about parallel lines, but no, not parallel lines rather. We're talking about 3 straight lines on a plane. When you're talking about a plane, we're talking about, of course, the Cartesian plane where we have Y, we have X, that is what we mean, X, Y. So we could have, if you have, let's say, L1 that way, then you have L2 that way. Look at this. And then you see this one is L1, and then this one is L2. And then you're told that now, okay, you see L3 is perpendicular. Oh, that is not anywhere close to perpendicular. Let's make it better. Let's have this. Let's say, oh, that is not even perpendicular also. Let's have, okay, maybe we could have, let me have that. Suppose, let's say, you see this as sketch. These are two perpendicular lines. This one is L3. And then you see L2 is perpendicular to L3. Now, is L1 perpendicular to L3? See, L1, this one is how we write L1 is perpendicular L2. This symbol here represents perpendicular to. If that is the case, and L2 is perpendicular L3, L1 is not perpendicular to L3. It is not perpendicular to L3, as we can see here. When you were to sketch, of course, you see this one is not one of the nicest, one of the best sketches. You see that sketch, you see this one should be, you see, sorry. You see this one should be, the x-axis should be that, y-axis should be that way, yes. But you can see this is L1, L2 perpendicular, and L2 is perpendicular to L3. There is no way that L1 is perpendicular to L3, and therefore that relation is not transitive. And that is exactly what we're talking about here. You can see that. I think you can see that clearly, yes. That is why we're saying that yes, determine whether R is transitive or not. You clearly see that that is not transitive. Yeah. Now let's go to C, another example. Now here you are asked to prove that if R is transitive, the inverse relation is transitive. Look at this carefully. Now this one is the solution, of course, in the form of a proof. Let R be defined on the set A. If it is defined on the set A, let A, B, C, because we're talking about transitive, there is need of A. Then, of course, we've been told that R is transitive, so we assume, suppose R is transitive, you see, if I suppose R is transitive, and therefore, what does it mean? So, it means R is, A is R related to B, and B is R related, that if A is R related to B, B is R related to C, then A is R related to C. That is what we mean by this. Remember the proof techniques that you were taken through on the basic mathematics. There are two. Remember, this one is a theorem. If R is transitive, then the inverse relation is also transitive. So what you're supposed to do is to have here we use the direct proof. You stick to every truth about this. Use the fact about this. Use all facts about this to cross over to this, and that is why we are assuming that R is transitive. And we must interpret what R is transitive is. R transitive means that if A is R related to B and B is R related to C, then A is R related to C. But now, what we know is that because the condition for determining whether, I think this is something that you know. Let me see that. Yes, of course, we are referring, not really, forget about that. We're talking about R inverse. Therefore, that R inverse exists. And that being the case, then R inverse, what does R inverse do to this? B is R inverse related to A, this one. C is R inverse related to B, this one. And also, based on this, C is R inverse related to A. That is exactly what we mean by all these belonging to the relation R inverse. Now, what you need to do is you need the connector here, the connecting point. You see this one is B, comma A. You have this one is C, comma B. So the ordered pair CB. So you should rearrange. You start with this CB, so that followed by B. So you can see this is what connects. Just in the same way, like in this case, you can see that is what was connecting. This one is the case. If that is the case, then C, you see this one is R inverse related to A, also R inverse related to A. And you can see this, implying therefore that if C is R inverse related to B, and B is R inverse related to A, then C is R inverse related to A. And therefore, R inverse is transitive because this is what satisfies transitivity of a relation. Let's go to equivalence relation. When do we say that there is an equivalence relation? We say that a relation R on a set A is called an equivalence relation on A when R is reflexive, symmetric, and transitive. How many properties? There are three. Any relation that satisfies these three properties is called an equivalence relation. And you're going to come across equivalence relation by the number of instances. And from now onwards, you're going to some of the relations is linear algebra. And I think you know you do linear algebra. And there you're expected to know how to show that a certain relation is an equivalence relation. And if I'm not wrong, I think you remember, if I can remember, what was that all about? Anyway, let me not talk about it. After all, you haven't gotten there. Yeah, so it is usually denoted by this. Look at this, wiggle, this symbol, wiggle. You notice just like the one for negation, if you remember, the mathematical logic. Yes, and let's have a look at the first example. If A is the set of all triangles in a plane, and R is the relation, that is A is related to B, if triangle A is equal to triangle B, meaning therefore that we're talking simply about the area of the triangle A. If two triangles are equal, and it means that the triangle, the areas are the same. So that is the area A is related to B. Area of triangle A is equal to area of triangle B, then prove that R is an equivalence relation. Here, we must show reflexivity. Every triangle is equal to it is equal to the area of the same triangle. So a triangle is related to itself in this case. The area of the triangle A is no different from the area of triangle A. So for every member of, you see, the members of A are just triangles. This is a set of all triangles in a plane. And therefore, we conclude that R is reflexive, and therefore we are done with the first property, reflexivity. We go for symmetry to show whether that relation is symmetric or not. What do we mean by symmetric? If the area of triangle A is equal to the area of triangle B, is it true, therefore, that the area of triangle B is also equal to the area of triangle A? It is true. So for any, look at this AB, where AB is. Area of triangle A is related to area of triangle B, or meaning in this case, our relation, of course, is equal to. Then there is no difference as to which one we start with. Triangle A is equal to triangle B is no different from triangle B is equal to triangle A. And therefore, B is related to A. And by that, we confirm that it is symmetric. The last part that we're supposed to show so that we confirm that this relation is an equivalence relation or not is by determining transitivity. And we pick three triangles in A, where the first triangle is equal to the second triangle, and the second triangle is equal to the third triangle. And that is exactly what we're doing here. A is equal to the triangle A is equal to triangle B is equal to triangle C. If that is the case, then triangle A must be equal to triangle C. And that is it. You can see this. Triangle A is equal to triangle B. Triangle B is equal to triangle C, implying therefore triangle A is equal to triangle C. And therefore, A is related to C. And that being the case, therefore, we conclude that R is transitive. And because R is transitive, symmetric, and reflexive, we say that it is an equivalence relation. Let's look at this one more example. We let A be this set of 0, 1, 2, 3, and that goes on. And R relates two members of A in a manner that where the difference of those two members is a multiple of 3. That is what we mean by thrice K. If and only if, yes, X minus Y is divisible by 3. Divisibility or multiple of 3 means the same thing. Then you're asked to prove that R is an equivalence relation. The first case is reflexivity, where we have X related to X. X is related to X if we have X minus X, which is equal to 0. Now, is 0 a multiple of 3? Yes. 0 is the same as 3 multiplied by 0, and therefore reflexivity is satisfied. In the case of symmetry, we are supposed to check whether if X minus Y is thrice K, is Y minus X also thrice another integer? Let's see. X minus Y is equal to thrice K. You factor out minus here. When you factor out minus, we shall have this negative X plus Y is equal to 3K. And now divide both sides by negative, and then rearrange these ones. We shall have Y minus X is equal to negative 3K. And then Y minus X is equal to, you factor out minus, you factor out 3, sorry, you have negative K. And of course, this one also is another integer, being the case, therefore, we see, therefore, that Y minus X also is divisible by 3. And that being the case, it means, therefore, that Y comma X is also in R. And therefore, what is satisfied here? Symmetry. Symmetric relation. We started with X minus Y is equal to 3K. We get to the point where we have Y minus X is also, that is, this one is equal to 3 negative K. And therefore, Y Even I think this is not how we should have that. This one should be y comma x, just like what I've done here. This is how it should be. That is an error. That is how it should be. This part should be that way. Now, looking at the transitivity property, all we need are three elements of A. Yes, 3 elements of A. And what we call those as X, Y, Z. And that is exactly what we have here. And now we would want to see if X is related to Y and Y is related to Z, then X is related to Z. X, Y in R and Y, suppose this is the case. We could even have this here. Suppose. You see, suppose that is the case. Then we see what does this mean and what does this mean by this definition of the relation. We see that we have X minus Y is equal to thrice K1. We have K1 here so that we have a variation. Y minus Z is equal to thrice K2. Now, when we have these two on the left-hand side, we're going to have these. And then the right-hand sides will be, we factor out 3 into K1 plus K2. 2 integers added together is another integer, and therefore we're going to have another K here. But now this one, negative Y plus Y is 0, and therefore we shall have X minus Z is equal to 3K. It means, therefore, that X comma Z is in the relation because it is in the form X minus. The other one is equal to thrice, which is the divisibility. And that satisfies exactly the definition for this relation. So that being the case, we see that R is transitive. Now, transitivity, reflexivity, and symmetry satisfied means that R, which is defined by this, is an equivalence relation. I think I was thinking of taking you through this other one. I think we're going to do this next time, representations of relations. We have representations of relations here. We have 10 minutes. I think that is more than enough for this evening. We're going to start from, that is representations of relations in our next meeting. And I think that is, God willing, on Monday. See you on Monday. I think we may as well call it a lecture up to there.